right? Can you see my screen?
Yes.
Does it look good?
Yes, great. Okay, so our next speaker is Dr. Mauro from Lawrence Berkeley National Lab. Mauro, the floor is yours.
All right, thank you everybody, and thanks again for the organizers for putting together this cool virtual this year. And in this short talk, I'm gonna just introduce you to the BerkeleyGW software package, which is gonna be used in the next day and today for your tutorial. And the outline of the talk is shown here. I'm going to start with a short introduction and motivation, and then I'm going to give you an overview of the BerkeleyGW software package, and then finally a little bit more details about the GW and BSc workflow implemented in BerkeleyGW, as you're going to use in the tutorial to finally summarize with the main result and conclusion of the talk. So let me start with a brief introduction. You probably know that most of the material science and chemistry application that you are running on a supercomputer all around the world are among the most heavily used on this kind of facility. And some of these names might be familiar with you, names like software packages like VASP, Quantum Espresso, QMCPack, NWChem, BerkeleyGW, CP2K, and so on and so forth. And the reason is that by running this kind of software, you actually get a very important understanding. You get a very well description and understanding of the fundamental electronic and property of this kind of material studying. And these are kind of very important in order to understand and design novel components for new devices with many applications which range from quantum computers to batteries, photovoltaics, catalysis, and so on and so forth. Now, density functional theory has been for a long time the kind of workhorse for this kind of application. And the reason is that density functional theory gives you an excellent compromise between computational efficiency and accuracy. On the other hand, density functional theory is a ground state theory, so often it doesn't really gives you a good description for the excited states phenomena. And in this case, you have to look to something which is more accurate, and usually just means that you need to increase the level of accuracy, which also implies that you have to usually increase the computational cost for your calculation. And this is exactly what GW and GW plus pedestal operator it is. Once you shift the focus from the ground state properties, which means in this case the blue part of the spectrum, to the excited state properties, which are those which are of interest for like complex materials, for example, you need to go beyond density functional theory and look to something maybe, you know, relatively based on many body perturbation theory, like GW and GW plus pedestal operator equation. So this means that this kind of approaches allows you to get an accurate description of the red part of the spectrum, so the part which is unoccupied, so the part which is related to the excited states phenomena of the material itself. Here is shown like an example is a dye vacancy point defect on silicon, on crystalline silicon. This kind of system are kind of prototype for solid state qubits, for which you need to have a good understanding of what's going on the ground state, as well as what's going on the excited states part of the spectrum. So density functional theory is not enough. You have to get a description, which include also an accurate description of the excited states part of the spectrum. Now, I told you about GW plus BSc. Probably the state of the art is one of the most effective and accurate approaches in order to predict the excited states properties of materials. But sometimes, GW and BSc get like a bad rep. It's like perceived as prohibitively too expensive in order to be applied to ordinary kind of application. And as we have seen before, like it seems like almost impossible to apply to system which are large enough, or so large that contains 1,000 or tens of thousands of electrons in the unitary cell. So that's why, I mean, our group of developer in BerkeleyGW is trying to push forward the possibility of this kind of methodology. And two ways to do that is to improve, the state-of-the-art kind of implementation in order, for example, to introduce approximation to reduce the time to solution, as well as the non-favorable scaling with the system size, and as well improve the implementation in order to scale up to leadership class HPC facility in order to study more complex material, or simply just to increase the system size we are able to tackle at the actual stage. We are working in general to improve the implementation in such a way that doesn't requires you a supercomputer to run, but you actually you can run this kind of simulation and this kind of calculation from your laptop. And then we try to keep like a well-maintained and tested, documented production quality set of software in order for everybody to use them, and as well for everybody to be able to contribute if they have any idea. All right, so let me give you an overview of the software package we're going to use today and tomorrow. And here is a little bit about the kind of design and the kind of vision we have in developing our software package. We start, of course, with a density functional theory mean field. So we need to run ground state calculation, of course, before starting with excited state and all the other advanced procedure. And our vision is that there are a lot of density functional theory codes available, and we take all the best among all of them, and then we use like an intermediate layer in order to convert this kind of output produced by all of the functional theory code into a format which is suitable in order to be used by our software package, such that we can focus on our core business, which is the treatment of excited states phenomena based on many-body perturbation theory, so GW plus Bell-Soper equation and beyond. Now, here is a highlights of the software package. Was already briefly introduced in the talk before by Steven. So again, our vision is to support as many software packages as possible, and there's also like a tutorial. Well, not in this workshop, but it's possible if you have any of your favorite software package which is not supported by BerkeleyGW, but essentially if you follow like a very simple set of rules, you can essentially convert whatever is the output of your favorite mean field code to something that can be used by BerkeleyGW. So we for the actual stage we support a large set of mean field codes, and one of our strengths is that we can really support several kinds of boundary conditions. With different way we can handle the sampling of the brilliant zone in different kind of dimensionality. Of course, the 3Ds for bulk materials. A lot of work has been done 2D and 1D, as well as we can handle a molecular system by using some specific way to handle the Coulomb interaction. Again, we have specific kind of routines that can deal with specific like system types. so semiconductor, metallic systems, and metallic system. And again, we are using efficient algorithm and libraries that can scale up to hundreds of thousands of CPU cores or tens of thousands of CPUs, of GPUs. And again, as I was previously mentioned, and as I'm going to show you later, our software package is massively parallel. So we've been able to scale to large scale of computer nodes on leadership class HPC system. So some of the recent highlight on the version 3, which we're going to use today and tomorrow, we have introduced spin-orbit coupling in the calculation, exciton finite momentum in order to calculate the finite momentum Q, so the exciton band structure essentially. We have enlarged the possibility for different starting point at the DFT level, including hybrid meta GGA, DFT plus U, and so on and so forth. We had a release, and it's going to be more in the next release. Actually, the GPU implementation is going to be the turning point, as I'm going to show you later, in order to tackle very complex kind of calculation. And this is going to be essentially ported to the entire set of modules we have in BerkeleyGW, with a great benefit for the time to solution and possibility really to exploit this kind of accelerators in order to get like extremely complex system to be handled with excellent time to solution. Again, we are using, like, again, as I was mentioning before, efficient libraries for pre-exascale and exascale systems. So especially for I/O input-output kind of operation, we are using the HDF5. And we have introduced new feature in order to deal with the self-consistent calculation. And as well, we have improved the performance, the tool, and the documentation for all the user to be essentially more clear and accessible to everybody. All right, so in BerkeleyGW, we have 4 major modules. You can start, as I was mentioning, from whatever is your favorite DFT code, and there's a very simple guide in order to, if you want to interface any of your code into a format which is suitable for BerkeleyGW, you can do it. There's in the developer's guide a very simple set of instruction that allows you to convert whatever is the output from your mainframe code to a format able to be read by BerkeleyGW. And then we have these 4 major module, epsilon, sigma, kernel absorption. And the reason why we break down the GW plus BSC procedure in 4 major steps is that essentially computational efficiency. Each of these modules, depending on the kind of system you are dealing with, have very different parallelization strategy, data layout, memory requirement. So you better break it up in different steps so you can efficiently use the computational resources instead of, again, running the entire procedure from scratch every time. As well, as you can see, each of the module produce some sort of intermediates, and these intermediates can be used multiple times for different type of calculation. For example, if you want to use a different level of theory to calculate the self-energy in sigma, you don't need to rerun the epsilon calculation, which gives you the dielectric function, but you can just run that simple module in order to check, for example, different level of theory, or even just to assess the convergence. Now, here is the snapshot of the 2 modules. Sorry, over the 2 kind of how we split the 2 part for the GW plus BSC. So epsilon and sigma are the 2 modules which are carry on the computation of the GW, so the calculation of the quasi-particle energies, which then you feed in into kernel absorption in order to build up the BSC Hamiltonian, which you diagonalize, and you get the excitation, exciton properties, and so on and so forth. Now, synopsis of each of the modules. Epsilon, as the name says, calculate the epsilon function, so it's the dielectric function and the corresponding frequency dependence. Sigma use the dielectric function in order to calculate the screen curve interaction build up the Dyson equation, solve it in order to get the quasi-particle energies, and then kernel use the information from the quasi-particle energy. Well, actually use the information from epsilon from the electric function in order to calculate Pedestal-Petter kernel matrix elements on a coarse grid, and absorption takes all the information together, interpolate from the coarse grid to a fine grid, the kernel matrix element as well as the quasi-particle builds up the BSC Hamiltonian, diagonalize the BSC Hamiltonian in order to calculate essentially the optical absorption spectrum. And in the tutorial today, you're going to use all of these modules. You're going to start with epsilon and sigma to calculate the GW band structure of silicon, and then you're going to use this information in the second part of the tutorial today in order to build up the BSC Hamiltonian and diagonalize it in order to get the absorption spectrum. All right, so let's get a little bit more into the details about the kind of computation that BerkeleyGW is doing. This is kind of important for for an audience to understand which kind of computation we are doing in order to tackle if you have a challenging system, understand which kind of computational kernels are implemented in the software package in order for you to more efficiently use computational resources and get your solution faster or is your final goal. So we run large distributed matrix multiplication over short-term matrices. We do a lot of linear algebra, so LU decomposition, matrix inversion, eigen decomposition of those previously mentioned. Non-distributed FFT, that means that we don't go over nodes to perform distributed Fourier transformation as usually pretty done on most of the FT code. Everything is like embarrassingly parallel and made at the node level. We do dimensionality reduction, tensor-like reduction for the computation of the self-energy, for example. And again, we have parallel I/O for the rank 2 and 3 and 4 tensor, the kind of operation we need to output in order to perform the entire workflow. Now, in terms of parallelization, we have 3 levels of parallelization at this stage. Over the nodes, we go with MPI. We have a very efficient multi-core implementation at the CPU level using the OpenMP programming model. And the GPU was introduced originally on NVIDIA hardware by using CUDA and HIP on the AMD hardware. These are dedicated branches which we use for development in order to ensure portability across architecture. On the main line code, we have our GPU offloaded implementation based on OpenACC and OpenMP type. All right, so the developers team, which is essentially giving you a summary here of what we are doing, has these kind of goals, and we want to distribute a highly performant production quality set of computational tools in order to use the GW and BSC method and make them available to you in a production quality way, essentially at the same cost or the same time solution as a DFT computation. In order to do so, we optimize our components on pre-exascale and exascale HPC system, but at the same time, we are looking into make these components available also to situation where HPC facilities are not actually available, and I'm gonna have a couple of slides on that. Of course, we are always looking to integrate new feature and developments from anybody that wants to contribute to our software package, and we like to keep like a close connection with our developer and user community. And this kind of situation like these workshops are a great opportunity for us to showcase our software package as well as get a feedback from the user how we can improve and how can we push forward and get a closer connection with our community. All right, to summarize this is like a plot that shows how by essentially developing our software package on increasingly more powerful HPC facility and make it like possible to exploit this kind of increasing computational power, how we have been able to clinch essentially the system size we are able to tackle with the Moore's law that describe the exponential growth of computational power over time. And here we have been shown that basically like 30 years ago or so, we were able to handle maybe 8 electrons, and by just keep optimizing our application, we have been able to extend the applicability of GW and DSC up to systems that are 11,000 electrons and almost 3,000 atoms with excellent time to solution for systems that were not even thinkable just a few years ago. And this is just the software development part of our software package that we are trying to bring to a broader audience and not only for experts in the HPC and so on. All right, so let's get in a little bit more on for the details about the modules of BerkeleyGW we're going to use. Again, GW is epsilon sigma, and the DSC part is kernel absorption. So let's start with the epsilon and sigma, which are the part which handle the GW part of the work. So it was already introduced before by Stephen in his introduction. Essentially, what we are doing is to extract the dynamical properties of the electrons by solving a Schrodinger-like equation, which is known as the Dyson equation. And here is just a sort of a single particle equation where the essentially complicated interaction among the electrons, the quantum mechanical interaction, are described by an effective potential, which is known as the self-energy. Now, as was previously mentioned, the self-energy in GW is a very similar role to what the exchange correlation potential is serving in a standard density functional theory. The problem is that this kind of object is very complex, is very complicated, is a non-emission operator, is non-local, is frequency dependent. And in general, for all kind of GW application that constitute the bottleneck in the solution of the Dyson equation. So essentially, the evaluation of matrix elements of this operator are generally what constitutes the bottleneck of a GW implementation. So in BerkeleyGW, we tackle this problem using, by handling the situation in 2 different modules. The first one is epsilon, and the name itself tells you what this module is doing. It's calculating the inverse dynamic function of the system, which at the actual stage has a computational cost with scale with and 4th power of system size. And then once you have computed the inverse dielectric function, you can use it in order to calculate the screen Coulomb interaction and eventually the matrix elements, self-energy operator, which eventually you need in order to solve Dyson equation and get the quasi-particle energy of your system. So in general, sigma can range as n to the power 3 to at most n to the power 4. And this is what I'm saying here is that if you're just interested in the HOMO, LUMO, or the band gap, then this is just two particles, two quasi-particle you have to correct. In that case, is a cubic scaling kind of approach. If instead you need to, correct a set of quasi-particle in order to fit into the solution of the Bell-Sapir equation, then that's also growing linearly with the system size. So the number of quasi-particles you have to calculate grows linearly with the system size. In that case, the computational cost grows the same way as does epsilon, so it's the fourth power of the system size. All right, so let's calculate, or let's get a little bit more of the details about the epsilon. It's calculating essentially the inverse of the dielectric function. In order to do so, again, we take into input as an input the wave function, the band energy, Q points, and a set of essentially frequencies. And the first kind of computation is essentially as many of these material science code performing fast Fourier transformation. In this case, we calculate intermediate matrix elements between our wave function basis, valence and conduction, and these auxiliary plane wave bases that instead we use to calculate the polarizability and the dielectric function. Second step is to calculate the RPA polarizability, and to a very simple, very oversimplifying this kind of procedure. This is nothing more than a big matrix multiplication over shortcut type matrices, and this is actually the bottleneck for large scale application. Once we calculate the polarizability and the frequency dependence of the polarizability, we essentially just perform a series of matrix inversion in order to calculate the inverse dielectric function after scaling with the Coulomb interaction. And again, for very large application, the chi0, you won't see it today because we are dealing with a very small system. Once you're going to get to more complex application, you're going to see that the polarizability, the calculation of the RPA polarizability is the bottleneck of the application, and is the kind of fine-tuning we've done, especially offloading on GPU, in order to make this step more accessible, in order to get it, to push forward that application of GW and so on and so forth. So here's the kind of snapshot of the kind of algorithm. So to give you an idea, for this kind of a very large application, this kind of short and fat matrix can be of the order of the 100,000 of rows and exceed the 100 of millions of columns. So this is a very expensive operation, both in terms of memory and computation. So we have been working around in order to make sure that this application works extremely efficiently on many core application, as well as once we offload to GPUs. I want to go too much into the details also because we have a new algorithm which is actually tackling the problem of the cubic scaling them. So here is the performance of epsilon. We are here showing on a multi-core architecture, 3 systems of increasing size. We go from a die vacancy in silicon with 214 atoms, then we essentially double the size to 510, up to 1,000 atoms, almost 1,000 atoms. And you can see that we can scale, linearly, pretty much linearly, over a wide range of number of cores, so multi-core interaction, multi-core architecture, and we essentially can reduce the time to solution to the order of minutes, depending on the system size, by using the appropriate number of resources. Of course, this scales much better on GPU architecture. This is an example of Summit, so the NVIDIA machine at Oak Ridge. We can scale up to tens of thousands of GPUs, and you can see how dramatically change and shift is the timeline. So essentially, really just tens of minutes or less than tens of minutes is enough in order to tackle system made of thousand of atoms and a few thousand electrons, up to, in this case, 2742 atoms. So you might be noting that, with the GPUs now, all the computation get extremely accelerated. If you look to this case and this case, essentially you get, like, with a comparable number of nodes, essentially at least like a 10x, so one order of magnitude improvement in the time to solution. The main problem is it was the memory, right? We have N4 flops. The flops became for free, and now we are stuck with like this N cube memory scaling, such that in this case, for example, in order to handle back then, a few years ago, this 1,000 atom system, we need at least 2,400 GPUs. So we have implemented a new version of the algorithm, which we call it like the MV block algorithm, which stands for blocking the valence band computation in the evaluation of the polarizability. This allows you essentially to break this huge matrix multiplication into blocks, for which you can actually control the memory available according to the memory that you have available on your resources. And essentially, you batch the thing and you repeat the communication cycle for each of these batches. And this really helps in order to effectively reduce the computational requirement of your memory from n cubed to n squared. And this really makes it possible to tackle like extremely large system, actually with very few hybrid nodes, having the GPUs essentially taking care of all the computation. Now we have this new algorithm that allows you effectively to use the memory in an optimal way, or suboptimal way, in the way because we're repeating the computation, but it doesn't goes out of memory, so you don't really need a huge amount of resources in order to perform this kind of computation. And this is shown here. These again, the epsilon scaling. We are now looking to a system with 214 atoms, and you see we can actually tackle this system with reasonable time to solution just using a single GPUs. And if we just now switch from the older to the newer architecture, so we go from the V100, which was the old Summit NVIDIA GPUs, to the new Perlmutter, which is the A100, you just take the full advantage of the memory increase and the flop increase that you get from the newer hardware. So this is like a win-win situation in the sense that you no longer need to have a huge machine in order to calculate, to do your kind of calculation. You can get it, and as soon as you get an improvement in the hardware, you immediately get the improvement and the time to solution your calculation. So on the right, maybe it's a little bit more complex as a plot in terms of scaling. So the strong scaling on the left just shows you how you can scale down, increase the CPU or the GPU's resources. Of course, you expect your time to solution to go down linearly, as is shown. The weak scaling, you clinch essentially the increase in computational resources with the the increase in computational effort with the increase of computational resources. In principle, the ideal scaling is constant, and essentially you see in this case on Summit at least, we essentially had a super linear scaling. So dealing with systems which are smaller cost you more than actually dealing with systems which are larger. So this gives you an idea that this new algorithm effectively really utilizes efficiently your resources. especially because we can now deal more efficiently with the cubic scaling bottleneck, and which is not bottleneck anymore. So the larger is your system, the more memory effectively you have available in a weak scaling sense, and the more efficiently the algorithm works. All right, so let's go back to the other part, the other modules of BerkeleyGW. So I've been talking about epsilon for a while. The second step after you have computed the electric function is actually the final step of the GW procedure, which is the solution of the Dyson equation, which is essentially implemented as the computation of a set of self-energy matrix elements that you build up in order to solve the Dyson equation given here. Now, there are different levels of approximation you can use. This is essentially the kind of formally exact formula with an integration of the frequency. And we have different approaches in order to deal with the frequency dependence of these kind of matrix elements. So the default is the generalized plus-Bumpol model, which is an analytical approximation to the frequency dependence. It's very efficient because it doesn't require the computation of the full frequency-dependent electric function, and require only the computation of the static dielectric function. The other method is the actual integration by using essentially numerical integration of the frequency integral. This comes with an increased computational cost because clearly you have to calculate the electric function of a multiple frequency, even though we have introduced like a method based on a low rank approximation of the static polarizability, which allows you essentially to reduce the computational cost for a full frequency calculation. Now, for sigma again, showing here is the kind of parallelization strategy, which is kind of important because for many applications we have seen that actually the sigma is the bottleneck for a GW plus BSC application. So the good news is that sigma has almost perfect parallel scalability, and the reason is that we have a two-level parallelization, which can be turned and is going to be turned in the future into a three-level parallelization, but there's more details for probably next year, for which essentially, since we have to calculate a set of self-energy matrix elements, we can essentially split it over pools of process, and each of these pools of process is essentially just independently calculate a set of self-energy matrix elements, and so essentially complicated communication happen within the pool communication, the pool parallelization, which in turn, if you really want to simplify the situation, is a sort of a matrix vector dot product kind of operation where the matrix itself depends on the vectors. It's a little bit more complex and is a sort of a tensor-like contraction if you're more familiar with this kind of terminology. All right, as I mentioned, sigma is a very good parallel scalability. It was already mentioned by Stephen before. This was the work we have done on many core architecture, the KNL partition, which has been just decommissioned a few days ago. So RIP to Corey. But we have been shown that we are able to scale to hundreds of thousands of CPU cores. So here is more than 500,000 for system made of 1,000 of atoms, more than 1,000 atoms, and also able to exploit, to reach high fraction of peak performance. In this case, on many core architecture, close to 50%, and achieving excellent time to solution for this kind of very large application. Of course, everything changed with GPUs, everything becomes much faster. And here we're just showing the result on Perlmutter, the successor of Corey at NERSC, GPU architecture. We actually have number as well on frontier, which is the exascale, the first exascale system in the pocket of the DOE. I wasn't sure it was I was able to show performance number out of frontier, so I decided not to put any slide, but be sure it's going to be available soon to the grading partner. So on the left, we can show that essentially we can scale up to the entire per matter GPU partition. I think it's a little bit south of 5,000 on something node. So essentially, Sigma can scale very well up to the entire system, as well as greatly take advantage of the acceleration provided by CPU, by the GPUs, as it shows here, how we step from the previous multi-core architecture, the Corey Haswell partition, into the new per matter GPU partition. If you just take the one-to-one node comparison, you essentially get a 2-digit X speed up. So your calculation get massively accelerated, just changing from one machine to the other and recompiling in order to use this new architecture. All right, so this is like what I was mentioning before, is how we can tackle the full frequency calculation. So all the calculation I've shown you before is essentially like based on the static, so the GPP model. And with this new method, essentially, which we have implemented, it allows you actually to tackle also the full frequency, where you actually integrate over the frequency in order to get the quasi-particle matrix elements. And in order to do so, we use an idea which was already around for a while, which is essentially a low-rank approximation of the static polarizability. The eigenvector of the static polarizability can be used as an alternative basis in order to expand the frequency-dependent part of the polarizability. And this gives you a quadratic speed up on the evaluation of the frequency-dependent part, such that the evaluation of a full frequency calculation is no longer n times more expensive than a static calculation, but this becomes like a 3x, 3 times more expensive than a static calculation. So you have to take into account the calculation of the static, which is going to be anyways done no matter what. Diagonalization, which is not scaling N4 but N3, but doesn't scale very well with the number of processes. And then you have the frequency part that you can reduce dramatically by 20x, as shown here, with essentially no difference in the result, as shown in the essentially the band structure as calculated with this static polarizability, so subspace approximation, as we call it, for silicon carbide. All right, time. I think okay. I have still like 10 minutes. So let's talk a little bit about the second part of the workflow. We have been talking a lot about the GW. Let's focus on the Bethe-Stefanel equation, which eventually is kind of simple in terms of implementation and computational details. So what we're doing is to build up a BSC Hamiltonian and then solve a BSC equation, which eventually is an eigenvalue problem. So we have a diagonal part. The diagonal part is the GW quasi-particle energy, which are calculated in the GW part of the workflow. So you need the G to solve the GW in order to correct your DFT eigenvalues in order to at least get a good starting point for the BSC equation. And then we have the important part for the BSC, which is essentially the two-particle interaction, electron-hole interaction, which we call it the kernel, which is handled, if you want, by kernel matrix elements. It's a dense matrix, so it's no longer diagonal, which builds up the remaining part of the Bethe-Stefanel equation. And once you build up the entire matrix, you're done. You just diagonalize it, and you get all the information you need. Excitation energy to build the optical spectrum, and the exciton wave function, which allows you essentially to calculate all the kind of cool properties that you want, the exciton wave function, area space, optical response, and so on and so forth. So very similarly to what we have in GW, we also can break down the computation bottleneck for the BSC, for the solution of BSC equation in two parts, which are implemented in two standalone modules, again, for computational efficiency. The first one is the kernel. We're going to use this as well today in the second part of the tutorial, which calculates kernel matrix element, and then the absorption, which takes in the quasi-particle energies calculated by the GW part of the workflow, and the coarse, also the kernel matrix elements calculated on a coarse grid, interpolate them on a fine grid, builds up the BSC Hamiltonian, and then diagonalize it in order to get the quasi-particle, sorry, the excitation energies and exciton function. So calculating kernel matrix elements is expensive, as well as calculating quasi-particle energy, but very similar to what we do in epsilon and sigma. We first essentially calculate these intermediate matrix elements between wave function. In this case, is not only conduction and valence, but we also have conduction and valence blocks. Once we have them, we just contract them. Again, you may over the screen Coulomb interaction in order to get the direct term, or over the Coulomb interaction, the bare Coulomb interaction, in order to get the exchange term. These are a little bit more details about the kind of parallelization scheme. The number of processes you want to use, essentially you want to have them proportional or being essentially equal, for example, to this kind of different level of parallelization. So growing proportionally to the square of number of k points. If the system is larger, then you want to be proportional to the square of the number of k point times the number of conduction band. And then to the lowest level, you essentially can go with the proportional to the square of k point nc and nv. So you can see that massive amount of parallelism we have for the evaluation of these matrix elements. We also have like a different scheme for handling the memory and the communication. High memory allows you to save the FFT, so it makes much faster the evaluation of the first step I was showing you before in this slide. And then the low communication also requiring actually a larger amount of memory, which allows to keep a replicated, copy of the dielectric function on each of the NPI rank, in order to avoid, multiple like NPI communication over nodes in the evaluation of each new matrix element. All right. So again, this was a kernel. And here's a little bit of the idea why we are using this interpolation scheme, which is becoming more and more clear recently. I mean, especially because converging with k point is extremely important, especially if your exciton is particularly the localized in real space. But again, very fine k-point sampling, and we have different strategy in order to reduce the cost of the k-point sampling by using smart way. We can chop it out and we can effectively sample some region of the k-space with method like the patch sampling or the non-uniform next sampling was implemented by Felipe and Diana. But again, calculating these elements on a fine grid is extremely expensive, as you can imagine. And of course, one of the solutions you can think about, and we have implemented, is essentially to fit or interpolate expensive computation on the coarse grid onto a fine grid. And here is the kind of prescription that we have implemented, and also the results showing on the right, which allows you effectively, essentially, to use pure information on the cross grid refit it on the fine grid in order to effectively converge your calculation as required in many applications on a very fine grid of K points. All right, finally, absorption needs to perform a diagonalization. These metrics can be pretty large, especially if you have a lot of K points, or if your system is very large, so you need to include a lot of conduction and valence states. We use effectively, for this kind of operation, of course, we don't want to reinvent the wheel, so we are using external libraries. Of course, ScaleUp is the default. ELPA has been shown actually recently to be able to scale to extremely large application of the order of millions by millions Hermitian matrices, which makes essentially with excellent solution, which makes our life very simple. But in case you don't need the full spectrum of, you don't need the overlapping vectors, you just need, let's say, the fewer, the 5% lower, just you are interested to a lower exciton, then we have also the solution to get using iterative solver, which is also ported to GPUs, and it shows like order of magnitude improvement in time to solution compared to direct solver. In that case, you just need, let's say, the fewest, like 5%, and this is gonna be much faster than actually a direct solver. And then we also have this Hadoop recursive method, which allows you to compute essentially the shape of the spectrum without accessing the information about the eigen. So some of the tools that we have, I've shown you that essentially we have the GW and DSC workflow, but again, one of the comments we usually have is like, yeah, but to converge your calculation, you're gonna have a convergence, a tutorial tomorrow about how to converge GW calculation. What we usually need is a large number of empty states. So everything goes very well, with the scale and everything. But one of the criticisms is like, yeah, sometimes our mean field code is not able to generate enough empty states because it was designed just to calculate the occupied part of the spectrum. This is not a problem. We have these tools, it's called parabands, which allows you to build up the entire DFT Hamiltonian in G space and just do a direct brute force diagonalization. Now, Felipe has been working a lot on this, and there are few other development which are very exciting, like pseudobands, which allows you to essentially contract the space of the virtual, but as well of the core states, so the deep occupied states, which is making essentially a GW approximation almost of the order of a cubic scale. And again, this is a big Hamiltonian to be diagonalized. Again, we are using external libraries. ALPA is being shown to be extremely effective and gain traction as well on GPU architecture. But there are on progress like spectrum slicing kind of approaches, which are embarrassingly parallel, and also embarrassingly parallel in this case in K point. So we are going to have today with an advance as a stretch goal for the today tutorials, but you can actually use this parabands tool in order to understand. And actually, we're going to use them. We're going to use it also tomorrow in order to effectively build up this Hamiltonian and have all these empty states for free available to check your convergence or to be sure that your calculation is fully converged. And here's some just performance timing. You see, we can tackle up to hundreds of thousand sizes for the Hamiltonian, and with 155,000, we're already talking about order of 1,000 or more atoms, depending on the pseudo potential of the cutoff. And just using very few hybrid nodes, we can get excellent time to solution just to start your GW calculation. All right, let me summarize I hope I didn't go over time. I think I'm still in. So I gave you like an overview of the BerkeleyGW software package, the kind of vision we have in the design, the structure, and the main workflow of the software package that you're gonna use essentially today, perform all the steps that you need to go from the SCF calculation down to the absorption spectrum. I give you an idea about the general algorithm we have implemented, the parallelization strategies, and the kind of computational kernels we implemented, and how we can gain traction on accelerator thanks to the specific kind of very, if you want, simple computation we are doing that we are being able to effectively translate on GPU architecture. And here is just a brief summary of the four major modules you're going to use. Epsilon calculated the electric function and the frequency dependence. Sigma solved the Dyson equation, starting, of course, from the electric function and calculating the screen Coulomb interaction in order to get the quasi-particle energy. The kernel calculate kernels and matrix elements on a coarse grid on the BSE Hamiltonian, and again, absorption in order to take care of business about the convergence of k-points, interpolates from the coarse grid to fine grid, builds up the BSE Hamiltonian, and finally calculate the absorption spectrum and all the optical properties. All right, useful resources. Here we have a manual. It's very easy to use, search over the input key. It's very user-friendly. And in case you have any problem building the code on your computer center, or you have problem, understand the output and input and so on and so forth, we have a mailing list, just mail in. And we are pretty fast to reply. 1 or 2 days usually is the time where we need to reply to the question in the mailing list. And the overview about the structure of the code, if you're more interested in the how you want to tackle like very large application, here are like the papers, which are essentially you can have a look if you are more interested in the kind of HPC side of BerkeleyGW. And again, to just conclude my talk, we are looking to the path to exascale. Frontier is here. Again, I wasn't sure if I could actually share any performance result out of there. They are looking good. So soon we are going to be able to run also on this extremely powerful machine, as we, thanks to the kind of work we have done before. And this is just a summary of the kind of HPC optimization we have done on GPUs on the previous, leadership class HPC GPU system, which was Summit, being able to scale to the entire system and achieving high fraction of peak performance. So 106 petaflop, a little bit north of the 50% of peak performance, and extremely good time to solution of the order of minutes in order to tackle system of tens of thousands of electrons. Yeah, so we are looking this, and the outlook looks good as we step into the exascale era, and we are ready to take it on from here. And with that, I think I reached my time limit. So thanks everybody, and looking forward for your question.
Thank you, Mauro, for the very nice talk. Since we're a little over time, so let's quickly go over all the questions, then we'll take a break. The first question is BerkeleyGW compatible with VASP?
Not at the actual stage. We need norm conserving pseudopotential. So we are compatible with a bunch of with open source software, but not yet with VASP.
Okay, so next question is actually regarding VASP GW. I ran silicon example in VASP by using GWBSE, but when I ran the GW with high core, like 36 or 72, it's quite slow than if I run with 2 or 3 cores. Any explanation or what recommendations do you have?
Right. So you're running silicon, it says?
Yeah.
Yeah. So, for silicon, you don't need as many resources as for other systems. It clearly, as you can see from many of these scaling tests, at one point you reach, the breakout is going to bend because you don't have enough computation to distribute to all the cores. So for silicon, you probably don't need to use more than a couple of CPUs or a single GPUs because there's no enough work to distribute to give to the to distribute to the GPUs or the CPUs. So the reason why it's going slower is just because all of your processes are just communicating among each other and not actually doing any work. So it's probably, I assume, it's going to be like your calculation is going to take like a few seconds if it's silicon on 100 cores. So yeah, you don't need to use a huge amount of cores for a calculation which is relatively small.
Okay. The next question is, ARPANET has own tutorials on GW and GWBSC. Will BerkeleyGW have something extra features than ARPANET or something else?
I'm not an expert on ARPANET. Maybe Jean Louis, you're a better person to reply to this question. As I said, we are focusing more on the ARPANET is a general purpose ground state first code, and we are focusing more on the GW plus BSC approximation. So I'm not an expert on ARPANET. I know that we can interface ARPANET to BerkeleyGW, so we are using whatever good ARPANET is doing as an input for our software package. But I cannot say at this point, what ARPANET is doing compared to what we are doing.
Okay, thank you. One last question. On your page 68, just clarification question. What does NP, NC, NV mean?
All right, so NP is the number of processes, so the number of NPI rank you're using. NK is the number of K points in the fine grid. In the coarse grid in this case. NC is the number of conduction band. So when you build up your BSC Hamiltonian, the size of the BSC Hamiltonian is equal to number of K points times number of conduction band that you're including in the calculation, number of valence band. So you have to think like the transition, you go from valence to conduction band, and then, of course, with the kernel matrix elements, you include the two-body interaction. This is on a coarse grid, so you have to think about the K points, so the sampling of the Brillouin zone that you're doing on the coarse grid, and then the interaction, the transition we want to include, essentially, if you want in an energy range. So you have a number of valence band, and then you allow electrons to go from this number of valence band to a number of the conduction band, and the product of these two times the number of K point essentially simply just gives you an idea how big your Hamiltonian is going to be. So NK number of K point, NC number of conduction band you allow the electron to be promoted to, and NV is the number of band that you include in the set that essentially you allow them to be promoted to the conduction band.
Okay, great. Thank you, Mauro. I'd like to thank Mauro again for your talk. And Roxana,
Stop sharing my screen.
You want to